In this lecture, what we would like to look at is the issue of self-inductance, right? And self-inductance is the phenomenon that arises when a circuit's own magnetic field opposes the growth of the current within that circuit, right? Now, a few preliminary observations, okay? Remember, first things first, that Faraday's law is written like this. Okay? The change in the magnetic flux is proportional to the induced electric, well, it's proportional to the induced potential, right? But that potential produces an electric field in a closed circuit. So, but notice first things first, all right, that we can also write the magnetic flux is going to be proportional to the current, okay? And you can justify this by thinking of a solenoid, right? So if I have, and let me actually draw it like this. Let me use the thicker one. Actually, you know what? Let's use a really thick one. Let's use this one. You know what? Let's make it even bigger. I'm sorry. I apologize. Let's make it even bigger. All right. So suppose that this has area A. Okay, so it will have cross-sectional area A, right? So when I'm staring down this, it's going to look like a circle, right? So this is a circular loop kind of viewed on its side here. And if I have, let's draw current in purple, for example. And if I have a small amount of current, let's imagine for a moment that the thickness of the purple line is indicative of the strength of the current, right? So if I have a little bit of current and it's flowing this way, what direction would the right hand rule tell us? If my current is this direction, then the magnetic field is going to be in this direction through the center of the coil, right? So if I were to draw, or if I were to push a much larger current through here, right? Then the strength of the magnetic field would be increased. So I would have a stronger magnetic field in here. And a stronger magnetic field implies a larger flux since my area is not changing. So this is where we can justify this statement that my flux is going to be proportional to my current. Okay, that is what the claim here is. And again, um, this flux would be the flux per unit turn. So if I have n turns times the flux through each turn, that will also be proportional to my current. Okay. And to get an equal sign here, what we need is a constant of proportionality. And we call that constant of proportionality L. Okay, so we call L the self-inductance of a circuit or of an element. Most notably, this should be no surprise, most notably inductors. Okay, now, if I, all right, well, first let's look at it this way. If I only, let's assume I only have a single coil, right? Then I can write my self-inductance like this. And I think that this statement here makes a little more sense. Okay, so this is just a ratio of two numbers. Okay, so your self-inductance is just a measure of the total flux per turn divided by the amount of current that it takes to produce that flux. So if you think about it, it should come out to be a constant because, again, if the flux depends on the current, then if I divide by the current, I will get a number. In other words, my current will cancel out and I'll just be left with other factors. So self-inductance in that sense is a little bit like capacitance, right? Remember when we said capacitance was just a geometrical effect of a system or a capacitor's ability to store charge, okay? The self-inductance is a element's ability to produce a flux per current. Okay, that's really all that's going on here. Now, if I put this back into this form, okay, now again, I'm just assuming one turn here, okay, where the flux now is going to be equal to Li. I want to connect this with Faraday's law. Whoops. I want to connect this with Faraday's law. And so I'm going to take the time derivative of both sides, but the time derivative of my inductance, L, is 0 because it's a constant. So it comes out of the derivative, and this would just be di dt. So what we can do is insert this into Faraday's law, and we would say E is equal to negative L di dt. So another statement of Faraday's law would be that your induced potential is going to be equal to, in magnitude, the value of the inductance of the circuit multiplied by the time rate derivative of the current. If my current is decreasing, okay, if my current is decreasing, then my potential is going to increase. And if my current is increasing, my potential is going to decrease. Now, this is the potential across the inductor. Okay? This is the potential across the inductor. Now, if your inductor is your only loop in your circuit and somehow you're causing a change in magnetic flux, then it will be the potential induced in the circuit. But if you have an external battery, such as in an RL circuit, if I have a resistor/inductor circuit with a battery, then this is not going to be the potential across the system. It will be the potential across the inductor. Okay. Now, for example, I want to derive an expression for the self-inductance of a solenoid. Now remember that the magnetic field of a solenoid is equal to mu naught Ni. Okay? The field is equal to mu naught Ni. Very, very simple magnetic field expression, right? Very simple magnetic field expression. So if I have a solenoid, and remember, n, lowercase n, is equal to the number of turns, n, capital N, number of turns per unit length. Okay, so whatever my n is, my lowercase n, that is going to be the capital N number of turns divided by my length L, right? So n is number of turns, and I would have a length L here. Okay? So I can write this as mu naught N over L times I. Now the flux, okay, the flux is going to be given by, remember, the flux is equal to the magnetic field times the area. And so the area of each individual circle here, the circular face, if I just generically say what the area is, so I'm not going to worry about a radius and get 2 pi r in this, I'm just going to use the area A. Okay. Then the flux through each face, all right, is going to be, or the flux through the whole thing, since we're counting, no. This is the magnetic field, right? This is the strength of the magnetic field. The flux through a single turn is going to be this. So the flux through a single turn would be equal to mu naught N over L times A times I. And then for all of the turns, whatever my N value is, the total flux through all of the turns would be mu naught N squared over L A I. Okay? And then the flux, I'm sorry, not the flux, but the self-inductance is going to be the total flux divided by the current, or mu naught um, N squared A over L. Okay. So this is the self-inductance of a solenoid. All right. So if you know what the cross-sectional area of the solenoid is, and you know the number of turns, and you know the length, then you can get the self-inductance. And by the same token, you could also write this as mu naught n a, where this is now again the number of turns per unit length, or n over L, and I have an n left over, a capital N left over, and that's where this comes from. So if I want to know the self-inductance of a solenoid, I need to know its total number of turns and its length and its cross-sectional area. Right? If I know those, I can plug those into here, multiply by the constant mu naught, and that gives me my self-inductance. Okay. Now, once again, recall that we have this quantity E is equal to negative L di dt. This is going to play a very important role in the RL circuit. Okay, and the RL circuit is what we are going to look at next. So, stay tuned. We didn't do anything terribly fancy here. Okay, I should say that we didn't do anything terribly fancy, but this is by far the most common shape for an inductor in a circuit. Okay, this is by far the most common shape for an inductor in a circuit, and it's because the solenoid, the coil, really does a good job of producing a strong magnetic field, even with small currents. And so the inductance is quite large for these shapes. Okay, much larger than for a single loop of current. If, for example, you have a very simple circuit like this, right? A regular battery, and let's say you have a switch here that's open, and you just connect this to a single resistor, and you complete the circuit like this. When I flip this switch closed, right, and my current starts to flow, if you have an ammeter in here measuring your current, that ammeter is going to measure your current relatively quickly, almost right away, almost instantaneously. Even though this circuit, because it's a closed loop and producing magnetic field, inside of the loop it produces a flux, and therefore it has some self-inductance. That self-inductance for a regular circuit like this is just so small, it's nearly negligible. Unless you have really, really thick wires with really large amounts of current, or you have a really, really large area. Okay. In either of those cases, then you might be able to start measuring it. But when you just have a battery and resistor, in nearly all cases, by far the vast majority, let's put it that way, the vast majority of cases, you're not going to measure the inductance if this is just a simple ohmic resistor. But when you start to introduce inductors in the terms of solenoids into your circuit elements, that changes, right? That changes. And so now you don't have a simple circuit, and that is what we're going to look at in the next video. All right. So stick around, and we will see you soon.